Can you guys hear me?
Yep. Yes.
Right. So I think we are live. Is that correct?
I believe so.
All right. Well, welcome everyone, and I do apologize for the background noise here. Can't do much about that, but my name is Matthew Rangen, and I am a senior project manager for EN Automation. Today we are going to be presenting another series in our webinar for power generation. Today we'll be presenting the PID theory, control, and real-world examples. If anybody has any questions during this webinar, please feel free to type them up in the webinar ask sessions, and we will address them as we get them. Alan, would you please move on to the next slide? So for the agenda, today we'll be introducing overall interest solutions, some of our services and what we do, the introduction to the automation power generation team. Two of the members here are specifically going to be presenting here. Alan will then be introducing PID control, describing how proportional integral derivative effect control. Tyler will be going over some basic PID applications. And then toward the end of it, we'll actually show some real-world examples of PID implementation. In this case, we'll use Rockwell software and Emerson Ovation. This is just a brief overview of interest by our numbers. Clearly, we are a big consulting firm, company that can do lots of things. I'm not going to go over all of these numbers, but just wanted to give you guys a brief overview of what our services and our breadth of knowledge. And if someone doesn't know it, I'm pretty sure someone else in this company does. And this is just a brief overview of the offices that we have in the United States, as well as one in Canada. The items highlighted in blue represent the EN Automation offices with staff nearby. Overall, this just projects that we have coverage throughout the United States, and we can support any needs out there. Next. This is a slide of our overall automation services. Clearly, we focused on control systems and electrical design work, but we can also do more than that. We can also do PLC, DCS, HMI software, SCADA system design, control system migration. That can be from existing systems, dated systems, even new systems to other systems. Overall modernization, one unique aspect is our control design and fabrication. We actually have a panel shop that can build panels. Drive control, we can help out with setting up VFDs, programming VFDs, upgrade roadmap development, phased approaches, turnkey system installations, commissioning and startup services, industrial and utility networking. We also support 24/7 technical support, depending on the type of support contracts we offer to our clients. Voltage distribution systems, we can do design work on that, as well as instrumentation systems. And outside of this, we also have other services that complement our power gen team really well, with turbine generator subject matter experts, as well as NERC PRC compliance needs. Next, please. So the EN Automation team has strategic partnerships throughout the automation industry. Some of these are listed up here, and we've actually got more than that. We actually have other partners outside of this as well. And if it's not listed here, I'm sure there's someone on staff that has experience with that system as well. So, all right, next slide, please. And I'm going to let Alan Burck introduce himself and start on the slides on that side. So Alan, please go forward.
I am Alan Burck. I've been with EN Engineering almost 4 years now. Prior to that, I spent 37 years at Duke Energy, always in power generation, always at a power plant. For much of the last 20 years, I've done mostly control system upgrades involving DCS applications. Prior to that was almost all PLC applications. So that's who I am. Anytime during the presentations, if you have any questions, like Matt had said, just go ahead and type something into the question and answers, and we'll address any questions as they come up. So today we're going to talk about PID control. We'll start with the basics. We've all heard the term PID control in the control world as a common method for automatically controlling a process, but not everybody really understands what PID control really is. So PID control is made up of three components. There's the proportional component, the integral component, and a derivative component. These following examples will illustrate each of these three components. Here we have operator Bob, who has recognized that the pressure is pretty far below the set point, and he needs to make some pretty good size adjustments to get the pressure back near the set point. So that's proportional control. Proportional control is the greater the error between the process value and the set point, the greater adjustment that he has to make to the output. As the error gets closer to zero, the contribution from the proportional control gets smaller and smaller until it reaches zero. So the goal of proportional control is just to keep the process value close to the set point. Jim here is looking at the trend. He sees that the process value it's pretty close to set point, but it's not quite there. So he doesn't really need to make any big adjustments. He just wants to make some small, fine adjustments. And that's integral control. It's a series of small, fine adjustments to match the process value to the set point. And the goal of integral control is just the fine tuning to match the process value to the set point and keep it there. The integral control slowly corrects the error over a period of time. So that's integral control. The derivative portion of it is probably the most famous, comes from the most famous control operator we all know, Homer Simpson. And Homer recognizes that the pressure is just plummeting, and he needs to make a drastic move to make the pressure stop dropping. It's often when we're talking about fuel, it's often referred to as a fuel kick, where we need to put a surge of fuel in to make the pressure stop dropping. So this would be the surge that Homer's thinking about. He needs to add, but we don't want to keep it there. We just want the pressure to stop, and then let the proportional and integral control take over. So after the initial surge, we'll let the derivative control die off. The primary purpose of derivative control is just to make the process value stop changing. So that's what Homer's interested in now. So that's proportional, integral, and derivative control, just the definition of what they are. Three different components, three different purposes, then they function and behave differently. The combined effect from the three is added together to perform the PID control. So no technical webinar is complete without talking about theory. So the theory behind PID control dates all the way back to 1922. Prior to then, control was done manually by a human. A human will make these continuous adjustments, would stare at the trend, stare at a process value, and make continuous adjustments. 1922, Nicholas Minorski, he was a control theory mathematician, a scientist, engineer. He was developing an automated ship steering control system for the U.S. Navy. And he did that by observing how the helmsman steers the ship manually. And he noticed that the helmsman would steer the ship not just based on the current course that it's on, but what corrections he's made in the past, the error in the error in the track of the ship and over time, as well as the rate of change. So the result of Nicholas studying the thought process that the helmsman put into how to make an adjustment to the course of the ship resulted in a mathematical model that incorporated that thought process. And this is a mathematical model that the Nicholas Minorski came up with. EFT is the error between the set point and the process value y of t. This error term is used, it's calculated and is used in the calculation for the proportional, integral, and derivative components. And then, as I mentioned before, the effect from proportional, integral, and derivative are all added together to form a single output. That output drives some field device that affects the process value. And that could be something like a pump, a valve, damper, some other field device that directly changes the process value. And as the change is made, a new process value will result. That's fed back into the mathematical model. New errors calculated. New proportional, integral, and derivative terms are determined, added together, and it makes an adjustment to the output, which then continuously updates and makes adjustments to the control device in the field. And this process just continuously, periodically loops around, recalculates based on what the set point is and what the process value is. The goal of it is to make this error term go to zero. So we'll talk about each of these individual components. The proportional term is simply the proportional gain, Kp, times the error term. So as the error gets smaller, the proportional term gets smaller and smaller. Likewise, as the error gets greater, the impact from the proportional gets greater and greater. Eventually, as the process value gets close to the set point, the proportional term will trend towards zero. And as the error term reaches zero, the proportional term is zero. There is no longer a reason to make any adjustments when the process value matches the set point. So Kp is the proportional gain tuning parameter that adjusts the magnitude of the proportional component of the PID controller in here. The integral term, this goes back to our calculus days in college, some of us many, many years ago. There's a integral gain that is a multiplier in the integral. So what the integral does is integrates the error over a period of time to eliminate the error. And the integral gain, Ki, determines the length of time that it takes for the integral to eliminate the error. Rarely enter the value as Ki. You rarely even see it that way because there's a time component associated with it, with the integral function. This is a change in error over a time. So normally what is entered is the time period Ti. That's the length of time that the integral function will take to eliminate the error. So Ki is typically shown as Kp times 1 over the integral time. Notice that Kp is the same, that's the proportional gain, meaning that as make changes to the proportional gain, it also affects the calculation of the integral term. And we also always have to be aware of those interrelationships between proportional, integral, and derivative components. The time component, Ki, it's implemented in a variety of ways depending on the manufacturer. Most of the time it's either entered as a time in seconds or 1 over the time, one or the other. Rarely will you ever see the integral gain entered as Ki. So the derivative component is acts on the rate of change of the process value, the rate of change of this error term. and it's the derivative gain times the change in error over the change in time. So just like with the integral function, derivative has a time component associated with it. It's the change in error over the change in time. So most of the time was defined as the derivative time. And notice that the derivative gain is often referred to as a proportional gain times the derivative time. So again, changing the proportional gain also affects the derivative function of the PID controller. Now, some manufacturers, they will separate the proportional gain from the derivative gain. So the proportional gain, changes in proportional, doesn't impact the derivative. You'll see that occasionally, generally not. So typically what's entered for the tuning parameters is the proportional gain, the integral time, and the derivative time. And it's always important to understand what the relationship is between the proportional gain and the integral component and the derivative component. So that's kind of a quick overview of the components of PID control, where it comes from. Does anybody have any questions at this point? I don't see any, but like I mentioned before, if you have any questions as we go along, please feel free to enter them in the Q&A and we'll address those questions. So we often hear the term tuning of a PID controller, and what tuning is making adjustments to the proportional gain, the integral time, and the integral gain and the derivative gains. Like we mentioned before, the integral gain Ki is actually Kp times 1 over the derivative time, and the derivative gain is Kp times the derivative time. So I can't emphasize it enough. Be sure to understand the relationship between these three. Question that always comes up is, well, how much proportional, integral, and derivative is needed to make good control? So there's a variety of methods that's used for adjusting these tuning parameters. There's a manual method, which is often just trial and error. You make a change manually, see what impact it has. There's analytical methods that you can use by analyzing the process response to a step change. There's also auto-tuning. There's auto-tuning software that will continuously evaluate the process and update the tuning parameters for you. So we're not going to talk much about the methods of adjusting or determining the tuning parameters. For now, we're going to talk about what impact each of these tuning parameters has on the overall PID control. So that'll be the proportional gain, integral time, and derivative time. There's 3 different scenarios that we can run into with PID control. It's kind of like the fairy tale Goldilocks and the 3 bears. One scenario is too much, one is not enough, and one is just right. So this scenario is the overdamped scenario, often referred to as not enough. The control is slow and sluggish. The control is referred to as being slow, and it takes the process value a long time to reach the set point. The solution to this scenario is to speed up the PID control by either increasing the proportional gain, the integral time, or the derivative time, or maybe all 3 of them, or a combination of the 3. To get the PID controller to correct the error faster. So that's what overdamp looks like. Say, classic case of it's too slow, the PID controller is not responding fast enough to correct the error. The other extreme is underdamped. This occurs when the PID controller gets to be too fast. It's making too abrupt of adjustment, and the result of it is the process value will oscillate back and forth across the set point before it eventually settles out. So this is the too much scenario, and the solution to this is to slow down the PID control by decreasing either the proportional gain, the increasing the integral time, or decreasing the derivative rate, or any combination of those to get the control to slow down a little bit. And then the critically damped response. This is a scenario of just right. All the gain factors are set just right. Control will overshoot the set point by a small amount. There'll be a small undershoot, and then the control levels out at the set point. So that's ultimately what we're looking for in the PID response. Another important thing to understand in PID control is this term, the process response time, before we can do tuning. It's important to understand the response time because the PID control just can't correct the error any faster than the process responds. And we'll see in just a few minutes what happens when we try to correct the error faster than the process responds. So to determine the process response time, we'll make a step change in the output and monitor the response of the process value. When this process value reaches 63.2% of its final value, that is referred to as one time constant. That time constant is the response time of the system. Now, in this example, the response time is 100 seconds. Question often comes up, just what exactly is 63.2%? Where does that come from? So it's actually comes from an exponential function. You can see this is an exponential function of the process value in response to a step change. The equation 1 minus e to the minus 1, that equates to 63.2%. That is the one time constant in the exponent is the response time of one time constant. By comparison, 5 time constants, the result would be 99.3%. If we go to 10 time constants, then the process value has reached 99.995% of its final value. So the response time is defined as the time that it takes for the process to reach 63.2% or one time constant of its final value. And we determine that just by making a step change, wait for this to reach its final response, and then find where that 63.2% value is. That's as fast as the process can move. And it's always important to understand how fast the process moves when adjusting the PID controller. We'll get to an example of integral control, and we'll see what happens when we increase or decrease the integral time to make the control faster than the process response. So first we'll start looking at the effect that increasing proportional gain has on the behavior of the process value. So we'll start with a scenario with the proportional gain way too small, and gradually increase proportional gain while we leave the integral and derivative components the same, so we can see just what impact proportional gain has on the response. So in this scenario, the proportional gain is not enough, and the process will take a fairly long time before it reaches the set point. If we increase the proportional gain a little bit, we'll see that the process responds faster and it reaches the error. The error reaches the set point, or the process value reaches the set point much quicker, but it's still too slow. So as we increase the proportional gain a little bit further, we can see that it's responding faster, reaching the set point faster. And we reach a point where we're getting close to the critical scenario, critically damped scenario. We're starting to see this first overshoot and a slight undershoot. So we are getting close to the ideal response of the PID controller. If we increase a little bit more, we can start to see that the first peak, the first overshoot, will get a little bit bigger. The undershoot will get bigger. So we are now beyond the ideal scenario, the beyond being critically damped, and we're heading too far beyond that. So we can see as we continue to increase proportional gain, this overshoot and undershoot will continue to get bigger and bigger. As we increase it even further, we'll start to see a second overshoot. And then increasing proportional gain beyond that, the second overshoot will get bigger. We see the second undershoot appear. As we increase proportional gain some more, it just continues to amplify the second overshoot and undershoots. As we increase it further, we'll start to see the third overshoot appear. And increasing proportional gain beyond that, the third overshoot will continue to grow. And as we get close to the point of instability, these peaks are getting closer and closer together. So when we reach, when we're at this point, if we expand the trend out, we can see that this takes 11 cycles before the process value levels out at the set point. And as we increase the proportional gain just a little bit further, we reach a point that each of these peaks are the same size. The overshoot and undershoot are all the same. The process will oscillate back and forth continuously at this, like this, forever, and it will never stop. So at this point, we're on the very verge of instability of the PID control. If we increase the proportional gain just a little bit beyond that, we will see that we drive the process to a point of instability where each of these subsequent peaks will continue to grow and get bigger and bigger. It will continue to grow, never stopping until there's some kind of intervention or something breaks. The only way to stop this is to put the control in manual to stop the PID control from driving the output too far. So the result of the root of this is the proportional control is trying to correct the error by too much at one time, and it drives the error too far the other direction. And then the error is greater at this point, and it drives it too far in the positive direction, and that just continues to grow and grow. So that's what happens when we increase proportional gain to the point that we reach instability. So we'll take a look at the same type of scenario with decreasing the integral time. So remember at the beginning, when we measured the response time, we saw that the response time of the process is about 100 seconds. We'll start with the integral time very slow at 300 seconds. So this process, the PID control is very slow at this point, and we see the impact. It takes a long time for the PID controller to match the process value to the set point. And as we decrease the integral time, we'll keep the proportional and derivative the same. So if we increase the integral time from 300 seconds down to 240, we can see that the response is improved, but it's still too slow. So we need to reduce it even further, further reductions, and it continues to improve. The process value is reaching the set point quicker, and it does require a shorter amount of time to reduce the error, but it's still not enough. When we reduce the integral time down to 150, we're now at half of the integral time that we started at. We started at 300, we're now at 150. So at 300, the process wasn't reaching the set point until all the way out here. Now it's out in here. Reducing the integral time in half will result in the process reaching the set point in half the time. So that's what we've done so far, is just we've cut the time and the integral time in half. We cut the time in half that it takes for the process to reach the set point. As we continue to decrease the integral time, the process value continues to take lesser and lesser time to reach the set point. Oop, I went too far. There we go. So we're now at the 100 second 100-second integral time, which is the response time of the system. And we can see that we have the ideal scenario of very slight overshoot, slight undershoot, and then the process levels out at the set point. We can push the integral time even shorter than that. As we do, the integral time will drive the output too far and will cause the process value to overshoot, which causes a greater overshoot and a greater undershoot. So we continue reducing the integral time. We'll see that these peaks just keep getting bigger and bigger until we reach a point of reducing the integral time now to 60% of the response time, and we start to see the second peak appear in the oscillation. Further reductions, we see the second peak grow. Reductions in integral time beyond that results in the third and fourth peak appearing in the oscillations. So once we get reduce the integral time down to 30 seconds, we reach the point where the process again is on the verge of instability. The overshoot and undershoot is the same on each cycle, and it'll continue oscillating like this forever. We have reached the point of instability of the PID controller. So what do you think happens now when we reduce the integral time even beyond that? It has the same impact as the proportional gain. Reduce integral time below the point of instability, the control becomes unstable, and these peaks will continue growing and growing until either something breaks or until there's some kind of intervention to stop it. So if we look at the two trends, they're very similar. Similar effect. Increasing proportional gain can drive the PID controller to instability. Decreasing the integral time can also drive the PID controller to a point of instability. So how do we tell which is which? If we look at the two side by side, this trend, it's the same time scale on both. This trend is instability as a result of too much proportional gain. The proportional gain acts faster than the integral time. This is the instability due to integral, and we can see that there's only 4 peaks in the same time period for integral instability compared to 8 peaks in the same time period for proportional instability. So typically we will see proportional instability occurring at a higher frequency than the integral instability, and that gives us a clue as to whether it's proportional instability that's causing the problem, or if it's the integral time being too short. So we've talked a lot about proportional and integral. Does anybody have any questions at this time? All right, last scenario we'll look at is the effect of increasing the derivative control, the derivative component of the PID controller. And just like before, we'll keep the proportional and integral components tuning parameters constant, and we'll change the derivative. We'll start out with zero derivative, no derivative effect. Sometimes you'll hear this referred to as a PI controller. So that just operates on proportional and integral, no derivative control associated with it. Make a step change in the set point. We can see that the output makes a step change. That's due to the proportional gain. When we make this step change in the set point, we see that the error is now larger than it was. The proportional control reacts to that and changes the output. Notice that the process value doesn't change for a period of time. Again, this is the response time of the process. So we've changed the output, but we're not seeing a change in the process value just yet, and we won't until we approach the response time. If we add a little bit of derivative control to it, we can see what happens is the derivative control sees a step change in the error term, and it reacts to that. The derivative control is the change in error over the change in time. It sees a large change in error over small change in time. So it has a large impact, a large response to that, but it doesn't last very long because the step change in the process or in the set point, it results in a a step change in the error, but after it makes that step change, the error is constant. So the error term, the rate of change of the error term becomes 0 again, and the derivative function dies out. And then just the proportional and the integral takes over. So other than that initial spike to the change in the set point, the derivative has very little response on the rest of the process. Some manufacturers will allow you to turn this off. In some cases, you don't want the derivative control to respond like this to a change in set point. So manufacturers will allow you to a selection to turn off the derivative control to a change in set point. As we increase the derivative time, we can see that this initial spike gets bigger, just because the gain term for derivative is the proportional gain times the derivative time. We've doubled the derivative time, so the response doubles in response to the step change. But we can still see that there's very little impact that that derivative impact has on the process further down. And we can continue increasing the derivative gain more and more. All that we see is this increase in the peak when the step in response to the step change of the set point. If we increase the derivative gain enough in relation, make it big enough in relation to the proportional and integral contribution, we'll start to see the derivative gain, the derivative function take over and start to dominate in the control response. So now we can see that as the process value starts increasing, it's starting to see a change in the error, and the derivative is responding by reducing the output. It wants the process value to stop changing. So we'll see that, and it's starting to have an impact by delaying the change of the process value, and it'll start taking longer for the process value to settle out to set point. If we increase proportional gain even further, this becomes more pronounced. A little bit further, and it becomes even more pronounced. We reach a point now that the derivative is becoming the dominant component, and the PID controller is having the dominant derivative effect on the process. If we go a little bit further, we can see how drastic the impact is from the derivative control. It doesn't want the process value to change, and as soon as the process value starts changing, makes a step change down in the output, which causes the process value to drop. And longer term effect is makes the quality of control less, and we can increase it even further, and it just keeps getting more and more dramatic. The PID emulator that I used to develop these examples limits the derivative time to 20 seconds. Many other applications will let you enter derivative time well beyond that. So you can imagine that if we increase the derivative time beyond this, it's just going to have a bigger and bigger negative impact on the process value, and the process value will just take longer and longer to reach the set point. The derivative really won't cause PID control instability, but it will result in really poor quality of control. So those examples just give you an idea of what impact changing the proportional gain, the integral time, and the derivative time has on the overall quality of control. Several conclusions to draw from these examples. Tuning skills develop over a long period of time. It takes a bit of experience, making a change, seeing what the impact is, trying something different. The challenge of PID control tuning is always to recognize the cause of the poor control and to know which parameter to adjust. So these examples hopefully will help you identify what scenario it is, whether we need to change proportional, integral, or derivative time. It's always important to understand the process and the process response time. If the process responds in 15 seconds, the control can be a lot more aggressive. If it takes 100 seconds, like our example, the control has to be slowed down. And the longer the process response time, the easier it is to drive the PID control to a point of instability. Something I meant to mention earlier is what I have found over the years is the vast majority of changes that people make to PID control tuning parameters is always to make the PID controller faster. And from all three of these examples, you can see that faster is not always better. So it's always important to recognize where we are and what impact a change in any of the tuning parameters is having on the process. Only change one parameter at a time. That'll let you isolate that changes to that parameter to understand the relationship that that parameter has on the response. After make a change, allow several minutes to stabilize after the change. Evaluate the performance. And then it's just like going to the optometrist. The optometrist will change the lens in his device, and the question he asks is it better or worse? And that's what we're looking for. Make a change to a tuning parameter, and you ask yourself, is the response better or is it worse? If it's better, you're going the right direction. If it's worse, you're going the wrong direction. So allow the process to stabilize, evaluate the response, determine what direction you needed to go next, and then make additional changes. It's always important to make several small changes rather than a large change. So you can get the idea that tuning can take quite a period of time, especially in a slower moving process. I generally begin with proportional gain. You can isolate the integral contribution by making the integral time very long. So as you make changes to the proportional gain, it's almost all proportional response is what you will see. So if you isolate the integral, you can adjust the proportional. If possible, make a small upset, see how the process responds. And we're looking for that a critically damp response where there's a small overshoot, slight undershoot, and then the process levels out. And then after you satisfy the proportional response, then you make adjustments to the integral time to as fine tuning to get the process value to stay right at the set point. I have found that derivative control is not needed in a lot of processes. Generally, it's used in slower processes, things like fuel control, boiler pressure control, steam temperature control, and boiler. Some of these responses, the processes have a response time in a range of 3 to 8 minutes. So as the process response time gets slower and slower, then the PID control has to become more dependent on derivative control. So we talked a lot, covered a lot of information. Like I said, the best thing you could do is experiment with PID control. It takes time. It takes some trial and error to learn what the impact that proportional gain has, proportional, integral, and derivative components has on a process. PID emulators is a good software tool that helps you gain experience with PID controlling and helps you understand the relationship between proportional, integral, and derivative and the process value. This is the website of the PID emulator that I've used in these examples. So I see there's a couple of questions. So one question was, must one measure process response time ahead to design the PID? Design-wise, no. Tyler's going to talk about some of these examples. But certainly before tuning, it's always important to know what the response time is. The PID controller will look the same regardless of the process response time. The way it's implemented logic, it will look the same. The difference will be the tuning parameters. So as the example showed, it's very easy to drive a PID controller into a point of instability. When you're doing the tuning, that's when it's most important to know what the process response time is. The other question is how many cycles of changes are typically required to reach steady state PID parameters. And the question is best to perform online. These questions will make some people nervous. Ideally, you need an upset in the actual process, the process in service. Need to create an upset to see how the PID controller responds to correcting the upset. So as if the process is just sitting there at steady state, there's nothing you can do with tuning because the PID control is satisfied. It takes an upset to make the error term grow to test the response of the PID controller. As far as number of cycles, it could take many, especially as the process response time gets longer and longer. I've literally spent days tuning PID control on a boiler with fuel control because the process is so slow. So unfortunately, there's not a straightforward answer. The difficulty is always that when the process is in service, customers really don't like to see upsets, but you have to see an upset to be able to adjust and tune the PID control. So I hope that makes sense. Patrick asked if the slides will be distributed. They are available. We will make sure that everybody knows exactly where to get to the slides. Anybody have anything else? So I know it's a quick overview. The intention of it is to just kind of give an introduction to PID control, understand the parameters, see some of the pitfalls that can occur. So anytime anybody has any other questions, please feel free just to contact me directly. Tyler, I think you're up next.
All right, yeah, I can take it from here. My name is Tyler Brown. I've been with Entrust Solutions for almost 4 years, same as Alan. I don't have quite the expertise that Alan has, I'll put it that way. Alan is the master, but yeah, all of my professional experience has been in power generation and automation, and tuning PID controllers it's an essential part of it. And kind of one of the questions that was asked is do you like to do this online or offline? And I think that kind of depends. Recently, we had a situation where implementing a new PID controller, and we were able to simulate some upsets prior to putting the system in service, and that can help you get kind of a baseline. And the more complex the system is, the more you're going to have to do tuning online, just because it's hard to simulate all the possible scenarios. But what I've seen, usually you can simulate some upsets before actually putting the system in service and kind of get a baseline of what you think the tuning parameters should look like based on your simulated upsets, and that'll get you close to where it wouldn't be unstable when you first put this new system in. And a lot of times when you're tuning, it's already an existing system and someone wants it to make it better than what they have right now. So in that case, you really need to do it online and see real-time results. So with that, we'll continue on with the presentation. So I'm just going to go over some basic applications that are pretty common that you would see. So this application here is a fuel oil pressure control. So the control is going to be through the control valve, which regulates the pressure based on whatever set demand signal. Usually the demand signal will be fixed at whatever that desired pressure is. and then your pressure may change based on how much you're using or things like that. So your set point is going to be a pressure demand signal. You'll have a pressure transmitter, 4 to 20 signal feedback. You'll convert that, say, to 0 to 200 psi, and your valve demand is going to be 0 to 100%. 0 would be closed, 100 would be open. So in this scenario, increasing your PID output, so the actual output from the PID, not the tuning parameters, the output from the PID, would result in a decrease in pressure. So this is an example of a really quick response loop. As soon as you make an adjustment to that control valve, you're going to see a pressure adjustment. So something like this, you want to keep in mind, you're expecting the result to be almost instant. So you don't want to set this up to plan on a 15-second response time. It's going to be much faster than that. So we can go ahead to the next example. So the next one will be a flow control. There's a couple of different ways that this is done. My example here, I did a VFD. This could be done using a control valve as well. But for the sake of this example, we're going to say this is controlled on a VFD to adjust the pump speed. So your set point is going to be a gallons per minute demand, flow demand. You'll have a flow differential transmitter, 4 to 20 milliamp signal. You'll convert that to gallons per minute. And that way you're comparing your gallons per minute demand to your gallons per minute feedback. And then your demand signal from your PID controller will be 0 to 100%. That'll be your VFD speed. 0 being stopped, 100% being 100% speed. So in this case, if you increase your PID output, you're going to get increased flow, whereas the other one was reversed of that. So again, this is a quick response loop time. When you increase the VFD speed, you're going to get increased flow. So this is another one of those. You don't want your response time to be very long. It could be a hair longer than the previous example. But in the scheme of things, this is going to be a very quick response time. And this is an example of a temperature control. So for this example, it's turbine lube oil temperature control using heat exchangers. So you're going to use a control valve to regulate the water flow into the heat exchanger, and that's what's going to control your temperature. So your set point will be an oil temperature demand. So you want your oil temperature to be fixed at whatever that determined value is, and you'll have a 4 to 20 milliamp signal from a temperature transmitter. You'll convert that to degrees Fahrenheit, same as your temperature demand. And your PID demand would be a 0 to 100% valve demand signal. 0 is closed, 100%, or 100 is 100% open. So with this, an increase in your PID output would actually decrease your oil temperature. So this example is a little bit of a slower response, and this will really depend on the design of the oil coolers. But it could be all over the map, whatever you see. But if the manufacturer says, just for example, it takes 10 minutes to expect a 1 degree temperature change, which probably wouldn't be the case, but then you would know when you're tuning your PID controller that you're expecting 10 minutes before you'd see temperature change. So if you set this up to be expecting a response in 10 seconds, then your PID controller is going to continue trying to lower the temperature and lower the temperature, and then all of a sudden all of your efforts will add up and put you kind of outside that stability range, and you won't be able to recorrect it. I don't know if there's one more example or not. Oh, yes. So this is a level control for a feed water heater. So this would be using a control valve to regulate water flow into the heater. So your set point would be a level set point, and you have a level transmitter. It would convert the signal into feet, and your level set point would be feet as well. Again, you'd be using a valve, 0 for close, 100 for 100% open, to control the level in the feed water heater. So in this case, an increase in the PID output would be a decrease in the water level. So this has a really narrow band of error. So in this example, you really need to focus on keeping it right at that exact level, because if your level rises too much, it'll rise into the extraction line. Otherwise, if it's too low, your tubes will not be fully immersed. So this is one that probably a lot of fine tuning at the level would be required, as opposed to some of the other examples. I think that's all I've got. Yep. All right, back to you, Alan. Or no, I think this is Matt.
Yep, back to me. So I know we've got 4 minutes left here for this webinar, so I will breeze through these examples pretty quick just to give the audience here any time to ask additional questions. So these slides are representing some actual applications using Rockwell, which in this case is RS Logix 5000. Just bear in mind I didn't use the latest version. It's just easier for me to extract some of this from the older version, but it's very similar, same structure. But overall, there's different ways of programming PID loops. In Rockwell Automation, you've got 3 different structures. You've got ladder logic, you've got function block, and you've got structured text. And inside of each one of these examples of programming, there's benefits, plus or minuses to each method. I won't dive into that for this webinar. That might be another webinar for us to develop, but I just wanted to give you guys a reference as to what to see and where to look at for a PID function. Go ahead and skip to the next slide. This is just an example of a ladder. We'll skip over this for now. Go ahead. Same thing for enhance. We'll cover this toward the latter half or latter end of my slides here. So go ahead. So one thing I want to make a reference is, as Alan and Tyler indicated, a lot of these PID loops and blocks use the same set. So it doesn't matter if it's pressure, doesn't matter if it's level, doesn't matter if it's flow, temperature, they all use the same instructions. It's just a matter of what the process variable you're trying to control and how are you going to control it via a control valve, pump, tank level, etc., or valve, etc. So you'll notice in here that all these examples that we're just going to breeze through pretty quick look exactly the same, even though they're different processes. So pressure, flow, temperature, level, they all look the same. It's just a matter of, as the Alan and Tyler were indicating, just different ways of tuning the process. So please go ahead and step through these slides. So this is the pressure, an example level. It may look slightly different, but overall it's the same functionality. Go ahead and go to the next slide, please. Flow, same thing. And next slide. So one thing we did not cover overall is the cascade PID loops. We just don't have enough time to dig into that right now, but it's another functionality that can help control more complex processes. And I'll just leave it at that for right now. But there are methods of using PIDs within PIDs. So continue, please. One thing I did want to focus on just real quick is the settings. As I mentioned, all these PID blocks use the same methodology, same programming. What makes them different is what the parameters are inside of these blocks. And this is the main differentiator for Rockwell, at least, is the fact that you can set up all these parameters in here. You can also change the control action. So, for example, some of the examples that Tyler was going over, 0 actually meant open, 100% meant closed, or vice versa. And that's where you can actually toggle that action of how the error is calculated. And same thing for calculating using proportional and derivative. Once we get further down here, I know Alan's going to go over really quick Emerson Ovation example that uses similar methodologies, but it's different as usual. So go ahead and go to the next slide. This is just an example of auto tuning. I won't go over it that well right now, but I just wanted everyone to be aware of there are auto tuning features in Rockwell. So I will hand this over to Alan to close this off.
All right, thank you, Matt. This is an Emerson Ovation DCS application of PID control. The biggest difference is Emerson separates the PID controller from the operator interface. So Emerson would add a, this is a manual auto station algorithm that controls the auto manual operation, set point, other parameters of the PID controller. And the functionality of the PID controller, this is just the calculations. This contains just the calculations of proportional, integral, and derivative. That's all it does. So everything that controls the functionality of the process is all done in MA station separate. So in the Rockwell examples that Matt went over, that's included or embedded in the PID algorithm. So you need to know what the functionality is and the differences and how to access it. The biggest difference between Emerson and Rockwell, we chose these examples just to highlight this. If we go back to the Rockwell example, we'll see that the tuning parameters that we have is proportional gain. We have the integral time, which is the unit of measure is 1/minutes. So remember that at the beginning we talked about the integral gain is a proportional gain times 1 divided by the integral time. So this is the 1 over time term that we enter for the integral component, and derivative is in minutes, but there's still proportional, integral, and derivative, which means that the integral component and the derivative component are both impacted by the change in a proportional gain. So with the integral, it is a proportional gain divided by or times 1 over the integral time. Derivative, it is a proportional gain times a derivative time. So the proportional change in the proportional gain does affect all three of these. In the Emerson world, Emerson separates the derivative gain from the proportional gain. So the derivative function is completely separate and independent of changes in proportional. Emerson has done that intentionally. The other thing that Emerson does is the integral time is in seconds. So this would be 40 seconds for an integral time, whereas in the Rockwell world, this is entered as 1/minutes of time. So the biggest thing to get from it is it's always important to understand how each manufacturer is implementing the PID control, because if you're thinking that Ovation uses 1 over integral time, the same as in the Rockwell world, it has a huge negative impact on the quality of control. So we could talk about this for a long time. Just really wanted to give you all a good overview of PID control, give you a good starting place. That's all I've got for today. Does anybody have any other questions, comments, any other closing remarks?
Yes, please. If there's any additional questions that come out of this too, feel free. We'll actually, Alan, could you move to the last slide that shows our contact info? Thank you. You can reach out to any of us. if you have any specific questions about PID theory, loops, tuning, application. We definitely appreciate your guys' time. Thank you for staying with us for the additional 5 minutes over. And thank you, Alan, for giving a great presentation. Same to you, Tyler. And if no one has any other questions, thank you. Have a good afternoon, and we'll see you guys on the next webinar. Thank you.
Thank you all.